I hope everybody is fine. In this video, I'll be talking about the very important topic. The topic is Heisenberg's commutator relations. And it's always advisable to have some insight into Poisson brackets. Because sometimes we can have a clear understanding of replacing uh, Poisson brackets with Heisenberg's commutators, uh, except there is to have some modifications. There is to have some more intrinsic understanding in Heisenberg's commutators. Now, the very first question arises in our mind is that what are these Poisson brackets? And these Poisson brackets are basically they are mathematical concepts. Suppose I have a Poisson bracket of Q1 and Q2, and so these Poisson brackets are mathematical concepts, and these concepts are more frequently used in classical mechanics to obtain the relationship between two physical quantities, say Q1 and Q2, and this Q1 can be position, this Q2 can be momentum, and they are denoted by these curly brackets. They are represented by these curly brackets, and they represent the degree to which these two quantities change together. And then the next important question arises in our mind is what is the difference basically between the Poisson brackets and a commutator? We have commutator in quantum mechanics where we have scatter brackets, and these Poisson brackets and commutators, say Q1 and Q2, these Poisson brackets and commutators, they are both basically the mathematical tools used to describe the relationship between the physical quantities. While in commutators that we have here in quantum mechanics, additionally, these Poisson brackets, what they do is they use classical variables such as position, momentum, energy, and while in quantum, in quantum commutators, what we call as commutators, we have operators. I mean, we have the operator of position, we have the operator of momentum, we have the operator of Hamiltonian, and then the question arises in our mind is that how are Poisson brackets, how these Poisson brackets are used in Hamiltonian mechanics. And in Hamiltonian mechanics, these Poisson brackets are used to determine the equations of motion for a system by calculating the time derivative of position and momentum variables. They are also used to define the Hamiltonian. These Poisson brackets can be used to define the Hamiltonian, which is a function that describes the total energy of the system. It's Hamiltonian. Now, there can be another question in our mind: what's the significance that we have, the significance of transformation property of these Poisson brackets? I mean, transformation property of these Poisson brackets. What they state is that brackets remain unchanged under certain transformations, and the transformations of coordinates and momenta. And what happens is that this property it allows us to use Poisson brackets to analyze the systems in different coordinate systems, or to perform some canonical transformations. And these Poisson brackets are related to Heisenberg's commutators. They are related to Heisenberg's uncertainty principle through the commutation relation between the position and momentum. And the uncertainty principle, as we understand, what it states is that it's impossible to simultaneously measure the exact position and momentum of a particle, and this is reflected in what we call as it is reflected in non-commutativity of the position and momentum operators in quantum mechanics. So what we have basically we have commutators, we have canonical commutation relations. Say if I take x, the position operator, and p as momentum operator. Now this is equal to I cross. This is the canonical commutation relation. And we have dq by dt equals 1 by I h cross q and h, and this is what is called as Heisenberg's equation of motion, where this q and h they are representatives of the operators. What they represent is the operators. So if I have to make a simple picture of the two cases, if I have something say p cap and q cap, this is a quantum commutator, and I should write this is a quantum commutator, and the Poisson bracket is p and q. So there is there's a close connection, at least from the fundamental picture point of view. And here what we have is we have Poisson brackets, and we can see that in Poisson brackets we have clear observables, we have clear physical quantities p and q, but when we see into the quantum commutators, we have the operators of those physical quantities. Now, when we write down the quantum commutator, say for position and momentum, this cap is the representative of the operator, equals I h cross. This h bar is the Planck's constant. And when we have to evaluate this, if we have to, what we do is, suppose we have x cap and p cap, it's always equal to a cap. It is x cap, p cap minus p cap, x cap. And this bracket is the representative of the commutator. So it is a commutator for the position operator and momentum operator. And what is important here is the order. We cannot change the order because these commutators they can boil down to matrices, and when we multiply the two matrices, they don't commute. So we have to take care of order when we are evaluating these commutators. And then corresponding to this this equation, this commutator equation, we have the equation of motion. What is that? That's dq by dt is 1 by I h cross. Say q and h being two operators. Then now this q can be any of the operators, and this h is the Hamiltonian operator. So what does this thing signify? That the rate of change of this q and observable, this is equal to 1 by I h cross the commutator of q and h, and then this equation is a representative of the equation of motion. Now, if for the sake of argument, if we take an example of a particle, and this particle has some mass, let us assume its mass is m, and we can immediately write down if it is in motion, if it is moving, then it must have force acting on it. And if we have to write down the total energy of this ideal system, we can write down the Hamiltonian. And if we write down the Hamiltonian in terms of position and momentum, and that's going to be the sum of kinetic energy of this particle plus the potential energy of this particle. So this Hamiltonian is basically the function of the position of the particle and is the function of the momentum of the particle. And this particle can be located in a phase space of position and momentum. So what we have, this x is the position of the particle. It's independent of the momentum of this particle, and this particle can have trajectories. And if we know the position and the velocity of this particle, all the future properties of this particle can be exactly predicted. So to say, we can think of force. M as m times acceleration. So t2, if this motion is along x, t2, and this is nothing but force, and this force can be written as the negative of the gradient of potential energy dV by dx. So what we have is we have Hamiltonian as a function of position and momentum, and we have a phase space of position and momentum. Now let us choose. Let's choose the two quantities. If I choose the two quantities, say for example, Q1 and Q2, and I have the Poisson bracket of Q1 and Q2, and this will be defined, and these Q1 and Q2 is the function of the position, and Q2 is the function of the momentum. Then we can write down this Poisson bracket as dou Q1 by dou X1, dou Q2 by, it shouldn't be x1, it should be x, dou p, minus dou q1 by dou p, and dou q2 by dou x. Now, if we think of this q1, if we replace this q1 by momentum of the particle and this q2 by the Hamiltonian of the particle, so we will have the Poisson bracket of P and H. So this is P and H, curly brackets. So for Q1 we have P, so this is dou P by dou X, and for Q2 I have H, so this is dou H by dou P, then minus dou P by dou P, then dou H by dou X. And we can immediately see here that this we understand that we have a phase space of position and momentum. This position is independent of the momentum of the particle, so this derivative will take this whole term equal to 0. And here this dou p and dou p will go, and what will be left with is dou h by dou x. But what is h? H is nothing but the summation of the kinetic energy of the particle and the potential energy of the particle. So for this case, for dou h by dou x, from this equation, this dou h by dou x will be dou v of x by dou x. That should be the case. So the Poisson bracket of the momentum and the Hamiltonian of the classical particle will give us what will it give us? It will give us P and H is going to give us minus dou v by dou x. And what is this dou v by dou x? It's nothing but force. So the Poisson bracket of the momentum and the Hamiltonian of that system is providing us the force. It's giving us the measure of the force. Now, to move on, taking the same case like the Poisson bracket of Q1 and Q2. And how do we write? Okay, how do we write the Poisson bracket? This is dou Q1 by dou x and dou Q2 by dou p. Then minus dou q1 by dou p and dou q2 by dou x. Now, in this case, let me choose for Q1 as the position of the particle, and for Q2 I'll choose the Hamiltonian of the system. So what will be the Poisson bracket of x and h? That's going to be, so instead of Q1 you will have dou x by dou x. And for Q2 this is dou h by dou p minus dou x. So for Q1 this is dou x by dou p, and for Q2 this is dou h by dou x. Now, exactly in the same fashion as we talked about the previous case, this x and p, they are independent of each other, so this term is going to go to 0, and this dou x and dou x will go. So the Poisson bracket of x and h will give us it's going to give us dou h by dou p. But the point is that what is this dou h by dou p? So for that we are going to write down the Hamiltonian. So what is the Hamiltonian? H is, it is p squared by 2m plus v of x. So now we have to take its derivative with respect to the momentum. So dou h by dou p will be, it will be simply 2p by 2m. This 2 and 2 will go, we'll get p by m, and p by m is nothing but the velocity. So this is velocity. And what is velocity? Velocity is dx by dt. That should be the case. Right. Now, so to move from here, what we have is, now let's think of using this what we call as the equation of motion for Poisson bracket of q and h. And what is that? That's dq by dt is equal to the Poisson bracket of q and h. Okay, so if this q is evolving with time, it's the function of position, and h is the function of the momentum. And we can write down this dq by dt as dou q by dou x. Okay, because what we are choosing here is that this q is it's the function of x and momentum. Right. So here we will have dou q by dou x, then dou h by dou x by dou t. We can use chain rule here. This is dou x. We can write dx by dt plus dou q by dou p, then dp by dt. All right, so I think these two terms, this dx by dt is evaluated, and this dp by dt is also evaluated because we had the negative gradient of potential energy, and the negative gradient of potential energy is the force, and force is also rate of change of momentum. So these two terms can be replaced. We can replace these two terms. So instead of so what are we going to get now is we will get dou q by dou x, then dou h by dou p, minus dou q by dou p, and dou h by dou x. So this is what we will obtain by taking the time derivative of q, which is assumed to be the function of position and momentum. So taking the time derivative of q, what we obtain is the Poisson bracket. This is nothing but the Poisson bracket of q and h. So what we have obtained is that this dq by dt is nothing but the Poisson bracket of q and h. Now, if this q, if this dq by dt is 0, now for this dq and dt to be equal to 0, so what we have the conserved quantity, and in that case, the Poisson bracket of q and h for the system is equal to 0. And this is the Hamiltonian version of what is called as Noether theorem. So this is the Hamiltonian version of Noether's theorem that we have obtained here. Now, proceeding from here, what we have is we have in Poisson brackets, in classical mechanics, we have dq by dt is equal to the Poisson bracket of q and h, right? And it has a corresponding replica in quantum mechanics as dq operated by dt is equal to 1 by ih cross q and h. So what is this q and h? This is the commutator relation between q and h, and this commutator relation is basically, it is q, this is q operator, h operator minus h operator, and q operator. Again, I'm using the same terminology that these operators and the basis of these commutators are matrices, and matrices generally do not commute. So the product here is not same. When you traverse the position of the two matrices, the result obtained is different. So here in Poisson brackets, now what we have q as the function of position and momentum. But here, in case of Heisenberg's equation of motion, we have the corresponding operator for this q. So we have q cap, and the examples for this q cap can be the position operator. This cap is a representative of the operator. It can be momentum operator. It can be velocity operator. It can be kinetic energy operator. It can be Hamiltonian operator, and so on, so forth, and so many things that can be attributed to it. And we can think of writing down this because the motivation here is to reach to the Heisenberg's commutator relations involving Heisenberg's equation of motion. And what we have here now, we have in Poisson brackets, we have dq by dt is the curly bracket q and h, where q is any observable and h is the Hamiltonian of the system. And corresponding to this, what we have in quantum mechanics is dq operator by dt is 1 by IH cross Q and H cap, commutator. And this is what? This is classical. This is the classical Poisson. We call them Poisson brackets. So this is a representative of the commutation between the two physical quantities. This is classical. And this classical is basically equal to 1 by IH cross. If we compare the two equations, then quantum commutators. I mean, here you have the Poisson brackets, here you have the Stab brackets. So this is how we can crudely understand the correlation between the classical observables and their corresponding operators in the quantum mechanics. And here what we have is, if I have, say for example, I have to write down the Poisson bracket of x and p. How will I write it? So there will be curly brackets. So this will be dou x by dou x, then dou p by dou p, minus dou x by dou p, and dou p by dou x. All right, so these are independent variables, so this will go to 0, this will cancel. So classical Poisson bracket gives us 1. And if we have to replicate this with the Heisenberg's version, what we are going to do, we can make this a small manipulation here, and we can think of 1 by IH cross, commutator of x cap and p cap is equal to 1. So this x cap and p cap is IH cross. And this is the very fundamental equation of the quantum mechanics and in terms of commutation relation, and this is Heisenberg's uncertainty principle. Now, moving on from here is so what we have is we have got some understanding about these commutators, and we have tried to interconnect the two because the idea of the commutator relation has certainly its origins in classical mechanics, but at the same time classical mechanics is not the fundamental theory. The fundamental between the two theories is the quantum mechanics. You can obtain classical laws from quantum mechanics, but the reverse is not true. Now, moving from here, if I have to write down the momentum operators, so say for example, I will take on first momentum operators. So let's assume that P is the momentum operator on a state vector x. So since this P is an operator, so this is IH cross dou by dou x for the state x. So this is my momentum operator on state x, and if we have to convert this this ket vector into the bra vector, we have to take the dagger of this ket. So taking the dagger of this ket will lead us to xp, and that will give us minus IH cross dou by dou x of bra of x. So this is our momentum operator that's being executed on the position, on the ket, on the basis vector of x. And we can have position operators now. The way we have momentum operator, we have position operator. Position operator. Okay, so I have position, and the state vector associated with this is the ket of p. So this is minus IH cross dou by dou p and the ket of p, and we can convert this ket vector into a bra vector. So we have the bra of p with respect to the position operator. So that's going to be the dagger of this ket operator. So taking the dagger of this ket operator will lead us to IH cross dou by dou p bra of momentum. So what we have is we have momentum operators on the position, on the state of position, and we have position operators on the state of momentum, or in the state of momentum space. Now, if I have to write down, say for example, I have to write down the commutation relation, the commutation relation. This is Heisenberg's commutation relation that we are talking about here. Say I choose the position x and I choose momentum p as the commutators acting on x, acting on the position operators on the state vector psi. So what we'll get out of this will give us xp of psi minus px of psi. So we can use the operators here. We can use the operator for momentum in this equation. So what we are calculating is the commutation relation between the position and momentum with the care of x on the state vector psi. So we can obtain from here is we will have x, then we will have minus IH cross dou by dou x of psi. Then minus, we will have minus IH cross dou by dou x of x psi. This will be the case because here we can see that when we use the operator for this momentum operator, now they are operators. I forgot to put the cap on them. They are the operators. So on writing down their commutator relation, we have x p psi. So for p operator, we are using the momentum operator, and here we have UV rule. So we can use the UV rule of differentiation here. So this is minus IH bar x dou by dou x of psi. Then this will give us plus. Then IH cross x as its dou psi by dou x. Then plus IH cross psi dou x by dou x. So immediately this thing and this thing is going to cancel. So this thing will cancel. So what we are getting is we are getting the commutation relation between position and momentum on the ket of x on psi, and we are obtaining IH cross psi of x. So we can generalize this Heisenberg's commutation relation as this. We can generalize it for the position state because I think it will be rather correct to write it like x and psi. Now we can do the same exercise. We can obtain the commutation relation for position and momentum, but with the ket of p and taking some other function, say phi. So what we have now is we have x, the position, and momentum, and the ket of p on a function, say phi. So what will we obtain from here is we will obtain xp, then phi of p. This phi is the function of momentum. This psi was the function of the position. This phi is the function of the momentum, minus p x phi of p. So we are going to use the same kind of story that we have used for position and momentum with the state of position. So we will have UV here, and here what we will obtain is IH cross dou by dou p, because we have momentum operator acting on the momentum wave function. So this is IH cross dou by dou p. Then we will have p of phi of p, and then minus we will have p IH cross dou by dou p of phi of p. So here certainly we are going to use the UV rule as we have used in case of the position space. Here we are using it in terms of momentum. So we are treating this whole problem in terms of a single coordinate. So the point is not in terms of the space; it's all in terms of the position of the particle, the position and momentum. Now, what we will obtain here is we will obtain IH cross phi of p plus IH cross p dou by dou p of phi of p, and minus IH cross p dou by dou p of phi of p. And these two terms will cancel, and what we will obtain is the commutation between position and momentum will lead with the state of momentum on the momentum wave function phi will give us it will give us IH cross phi of p. Or more generally, we can write it xp. P phi is IH cross ket of p and phi. So this is our Heisenberg's commutation relation between position and momentum when acting in the momentum domain. So we can write down this Heisenberg's commutation relation, since we are talking about the 1D case, one-dimensional case. So we can generalize this thing as the commutator between x and p. What it gives us is IH cross. And if we take this formalism in 3D, we can choke it in terms of, say, the commutation between xm and pn. Say, so this will give us a canonical delta function mn, I h cross, and I will be the identity matrix. So here for m is equal to n, what we will get this relation will give us I h cross I, and for m equal to n, what we'll get is this x m and p n will lead to I h cross and I, and from m not equal to n, this commutation xm and pn will lead to 0. So this delta mn is nothing but canonical delta function. I have a very bad handwriting. Canonical delta function. So this is what we started from Poisson brackets, and we tried to end up our presentation at the by discussing the Heisenberg's commutation relations. And we can generalize this Heisenberg's commutation relation in terms of the functions, and we can write down the result for, if I think it's better to proceed it for functions as well. So if I choose the commutation of some function f of x and momentum on the state x and psi, so what it will lead us to f of x and p of psi of x minus p f of x and psi of x. So certainly we are going to use the operators here, and what we'll get minus I h cross f of x dou by dou x of psi of x. And then here we will have for this, this will become plus, because the operator p will be operator p will be used here, so this will give us I h cross dou by dou x of f of x and psi of x. So here we are going to use UV rule again in the same way as we did in the previous case. So what we're going to get, minus I h cross f of x dou by dou x of psi of x. Then we will have plus I h cross dou f of x by dou x psi of x. Okay, then we will have plus I h cross, then f of x will remain as it's, then you will have the derivative of dou psi of x by dou of x, and we will have the cancellations. This thing will cancel with this, and we will obtain the commutator for a function, a generalized function f of x on the momentum operator is going to give us with the ket of x and psi is going to give us I h cross dou f by dou x, ket of x and psi. So this is the generalized form for Heisenberg's commutation relations. So better is to write down this generalized form. We can write down it for any function in terms of for position operator, and we can write it for momentum operator, and we can generalize it. So in 1D case, in one dimension, what we can write is, if we have a function of x and the momentum operators, they lead to I h cross dou f by dou x. And if we have the position operator and function of momentum, so this will lead to I h cross dou f by dou p. And we can generalize this thing in 3 dimensions also, and we can write down it in terms of 3 dimensions. So this is what I have tried to talk about something about the Heisenberg's commutators, and the motivation of making this video was to have actually a correlation of Heisenberg's commutators with the Poisson brackets.